Hello everyone, this is Mr. Swapnil Babusai Verawade, lecturer in Shri Institute of Technology Polytechnic Yatra Vichalkaranji. I am here with my next lecture on chapter number 6. Okay, so our next point is annealing process, which can also be called as a softening process. Okay, so here in this process we are going to soften the hard material, or we are going to decrease its hardness. Okay, so see, the subtopics in this lecture will be like, first point is what is my annealing process, second point will be a purpose of annealing process, then we have types of annealing processes, and then full annealing, or we can say it is a conventional annealing, and second one is isothermal annealing. So these 5 points will be covered in the today's lecture. Okay, so we will move forward. So in last lecture we had covered something about what is mean by heat treatment process. As you know, heat treatment process is nothing but it is something which is a combination of operations. It may be a heating, it may be a cooling, okay, or we heat or cool the material. Which material? It may be a metal, it may be a pure metal, it may be a alloy, it may be a solid, okay, but we heat the material below its melting temperature, because above the melting temperature that material can change its shape and size, and when we cool it, it doesn't gain its original shape and size. Okay, so we heat the material below its melting temperature only. Okay, so the heat treatment process is nothing but a heating of any metal or alloy below its melting temperature, or heating in a solid form itself. Then we hold the material at some temperature to get the homogeneous structure. Okay, and then we cool it in some mediums. Okay, we can cool any heated material in water, we can cool the material in air, and we can cool the material in furnace. Okay, on the basis of cooling we have the four types of heat treatment processes, as we had studied that: first annealing process, second normalizing, third hardening, and fourth tempering process. Okay, so annealing process, where we cool the specimen or cool the heated steel in a furnace itself, so it is an annealing process. If we cool the material in air, in a flowing air, it is a normalizing process. Okay, and if we cool the heated material in a water, then it is a hardening process. Okay, so the heat treatment process are mostly classified on the basis of what type of medium, what type of cooling medium, or what type of cooling rate we use to cool the material. It is about about the heat treatment process. Okay, so the first point, or the first type in heat treatment process, is the annealing process. Okay, annealing process is generally called as a softening process, because here we heat the material, we hold the material at some temperature for some time, and we cool the material in furnace. Okay, in furnace, at initial we heat the material, okay, at some temperature near about 900 degrees Celsius, 1000 degrees Celsius, and the same furnace we cool the material. So after cooling the whole furnace, that material inside the furnace will get cool, so it will so much time to cool the heated material. Okay, so it may be in the range of 30 to 40 degrees Celsius per hour only. Okay, so see, annealing process, here we have the slide. First point, annealing process. In that we have principle of annealing. Okay, so see, in very first line it is written like it is a softening process. Okay, so here we soft the hard material, because if you have so much of hard material, but as we know the hard material is a brittle one, we cannot have a good machinability on hard materials, because it may have the cracks, and that crack propagates and it have the failure. Okay, so we soft the hard material so that we can use it in the industries. Okay, so annealing process is a softening process first of all. Okay, then in which an iron alloy, what do you mean iron alloy? Iron alloy is a something, or we can have a best example of uh, iron alloy is a steel. So you can stay straight away as a steel. Okay, in which iron alloy or steel is heated to a temperature above the transformation range, that is above the 727 degrees Celsius. Now see, we had studied something about iron carbon equilibrium diagram in our second chapter. Okay, in that iron carbon equilibrium diagram we have some phases. like alpha ferrite, delta ferrite, austenite, cementite, ledeburite, perlite, and liquid iron. Okay, so in steel only we are going to see about only the two phases, just as a alpha ferrite, or you can say ferrite, and second about the austenite. Okay, so see, above the transformation range means above the 727 degrees Celsius, when you are hitting some material, it changes its phase from ferrite to austenite. So it is called transformation range. Means, take a simple example. If I heat the steel, at initial it have temperature about 20 degrees Celsius. It is a room temperature. Okay. So when I heat the steel from 20, if I'm going to increase the temperature 20, 100, 200, 300, 500, 600, and when I up to the 700 degrees Celsius, okay, 726 degrees Celsius, I have the ferrite phase in my material, okay. But when I cross the 727 degrees Celsius line, my ferrite phase will change into austenite phase, okay. Means this is the temperature, that is 727 degrees Celsius is a temperature where my phase of the material get changed. When heating, ferrite changes to austenites. And when we cool again material, because material never be on the same or never be on the high temperature for a long time, okay, it will cool naturally. And when we cool the material, means from 900 degrees Celsius to room temperature, that will again change from austenite to ferrite. Okay, so transformation range means it is a temperature at which phase changes on heating ferrite to austenite, on cooling austenite to ferrite. Okay, see, next in the diagram we also can see, okay, see here we have total three lines. First, this is a heating line, okay. From this, here is will be our room temperature, okay. It may be a 20-30 degrees Celsius. From this we are going to heat it as it is an inclined line. What it shows, that heating will take a time, okay. If we have a curve for on y-axis we have temperature, on x-axis we have time, then this will be the graph for time and temperature. Means this inclined line will show that for heating purpose we required some time, okay. Then when we reach this temperature will be more than 727 degrees Celsius, okay. At this temperature we cannot go higher from this, because there will be somewhere the melting temperature of steel, okay. We cannot reach up to this. We heat the steel just below its melting temperature, because we can't change the shape of the material, okay. So at this temperature we will hold the steel at same temperature for some time, okay, for to get a homogeneous structure. Because when we heat any material, it is first get heated from outside, it is not heated at the same temperature in inside also, okay. So have a same temperature at outside, and to have a same temperature at inside, at inner part, at inner core, we remain at the same temperature for some time to get a homogeneous structure, to get a uniform structure of a temperature throughout the material, okay. Then it may be for 2 hours, 3 hours, it may be for minutes, it may be for some seconds. It depends on the shape of material, it depends on the size of the material, and depend upon the temperature range, okay. Then after holding period we cool the material in a furnace, okay. So see, here we have three points: heating, then holding, and again cooling. See here we have written it is cooled slowly inside the furnace. So it is annealing process. When we cool any material in furnace, it is always called as a annealing process, okay. So here we have only three things: heating, holding, and cooling, okay. So we will move to the next one. See, what is the purpose? If we talk in general, okay, when I anneal the material, when I soft the material, what will happen in general? As we know, as I soft the material, its hardness will going to decrease. As hardness decrease, brittleness will decrease. As hardness decreases, its softness will increase, its ductility will increase, its malleability will increase, its toughness will increase, its machinability will increase. These are the general ways we can say, okay. So we have some few points, or we can say these are the purposes for what we use the annealing process. So first, to improve the machinability, okay, as we have softened the material, it will improve the machining speed, or it will improve the machinability. Next, to increase the ductility and toughness. What is meant by ductility? It is nothing but it is a property of material by which we can draw out the wires. We can form the wires for a material. If I form the wires for materials just like gold, then we have platinum, then those materials have the ductility property. So as we soften the material, it will increase the ductility and toughness. Next, it reduces the internal stresses. The internal stresses are developed where we have forging operation. Okay, means stress means something. Stress, it is nothing but force upon area. If I want to hammer on any material, means we are hammering, means we are providing the force on a material. That force, and we have some area, it induces the stress. Simple. Okay, so that stress would form any crack in material. Okay, so to avoid a crack, we must reduce the internal stress. So annealing process is for reducing the internal stress. Next, improving the mechanical, physical, electrical and magnetic properties of material. As you know, there are so many mechanical properties, just like a strength, then toughness, stiffness, ductility, malleability, hardness, brittleness, toughness, their creep, fatigue, all this blah blah blah. Okay, then physical properties are there, then electrical, magnetic properties. Okay, next, to refine the crystal structure. To refine the crystal structure means, as we know, there is something called as a grains, or a grain size, or you can say crystal structure, or we have the BCC crystal structure, FCC, or we have simple cubic crystal structure. Okay, so this process will refine the crystal structure. Next, it reduces the residual stresses from casting. In forging we have internal stresses, in casting we have residual stresses. The main reason to apply annealing process is to reduce the internal stresses, or to reduce the residual stresses. Okay, next, to remove the interrupted gases from casting. Yes, we can remove the interrupted gases which are formed during the casting process. Next, to improve the softness, as you know, this is a softening process, it will always improve the softness. Okay, next, to reduce hardness and brittleness of material. As it is a softening process, it will always reduce the hardness and brittleness of the material. So are the few purposes of the annealing process. We will go forward. So we have total 4 types. First is a full annealing, or you can say conventional annealing. Second, isothermal annealing. Third is a process annealing, and fourth is a spheroidizing annealing. All these 4 types are of annealing only. So means here we cool the material in furnace itself. Okay, in every type we cool the material in furnace, or we may cool the material in steady air, which have the same cooling time as that of the furnace. Okay, so in this lecture we will see the first 2 points, and in the next we will see the third and fourth. Okay, so we will move forward. That is our first point, that is full annealing, or we can say conventional annealing. See, as we had studied in the second chapter, that this diagram is from the iron carbon equilibrium diagram. Okay, on the x-axis we have composition, on y-axis we have temperature. Okay, see, from 0 to 1.6 means we are in the range of steel. Okay, as we know, steel have carbon percentage from 0 to 2%. Okay, so this diagram is taken as just a small content from iron carbon diagram. Okay, a small view we can say. Okay, see, from 0 to 1.6 means it is about only a steel. Okay, then we have temperature from 600 to 1000 degrees Celsius. So see here, this is 727 degrees Celsius line. This temperature line will be called as a 727, means this will be the transformation temperature line. Okay, below this line here we have the alpha Fahrenheit phase, and above this line will be the austenite phase. Okay, so see what we are written here. First, full annealing process is different for 2 things. Just first we have the for hypoeutectoid steel. What is mean by hypoeutectoid steel? The carbon from 0.008 to 0.8% carbon. So see, as we had studied in the second chapter, 0.8% here at this point, this will be a cross sectioning point. Okay, so at this point we have eutectoid transformation. Okay, so this 0.8% will be a eutectoid carbon. Okay, so from this 0, or we can say 0.008, from 0 point up to 0.8 we have hypoeutectoid steel from 0 to 0.8, and from 0.8 to 2% we have hypereutectoid steel. These are two differences. Okay, from 0 to 0.8 it is hypoeutectoid steel, and from 0.8 to next it is hypereutectoid steel. So we will going to first see for the hypoeutectoid steel. See, steel is heated above the upper critical temperature, it is A3 line. See, we had seen something in iron carbon equilibrium diagram that critical temperatures, total we have 5 critical temperatures: A0, A1, A2, A3 and A4, or you can say ACM. See, as we know, A0 is at 210 degrees Celsius, it is below. This 727 will be A1, 768 will be A2. This your from 910 to 727, this will be the A3 line. And from here we have again second line, and this line will be from 727 to 1147. This will be a ACM line. Okay, so for this point we have, this will be a A3 line. Okay, so see what I have written: steel is heated above the upper critical temperature line, that is A3. Means this green zone is nothing but the temperature zone. Up to this temperature we will heat our material. In this zone we will heat our material. Okay, so see, if we have any steel which have carbon percentage, here will be, we can say, we can assume a steel having 0.1% carbon, we can this steel up to this temperature, this zone. Okay, if you have something 0.3% carbon, here we can take. Okay, so this, for this we can heat it up to this, in this zone. Okay, that the temperature may be 850, 870. Okay, for 0.6% carbon steel we can heat it up to this temperature. Okay, this may be 800 to 780 degrees Celsius. Okay, so the temperature zone will be changed as per your carbon percentage. Okay, so steel is heated above the upper critical temperature line A3 by 30 to 60 degrees. This 30 to 60 is nothing but your zone. Means above this, here will be your 30 degrees Celsius, and this will be, line will be your 60 degrees Celsius. Okay, it is usually between the 727 to 910 degrees Celsius. Means from this up to this we can heat the material above that. Okay, next again same, we will hold the material at same temperature for some time to get homogeneous. Always see, always remember, we hold the material to get a homogeneous structure. Next, then it is cooled in a furnace with a slow cooling rate. Cooling rate will be 10 to 30 degrees Celsius per hour. And next, after heating, holding and cooling, we get coarse perlite structure. Perlite means it is alternate layer structure of ferrite and cementite. Okay, so the coarse perlite structure will be a softer one. Okay, then we will move to the next one. Here for hypereutectoid steel, means carbon from this 0.8 to 2%, we have this zone will be of hypereutectoid steel. Okay, so see what they said here: steel is heated above the A1 line. Okay, for half one we have this A3 line, and for this from 0.8 we have this A1 line, that is 727 degrees Celsius. So here from 0.8 to 2% we heat the steel above the A1 line. Okay, then again we hold the steel at same temperature for some time to get homogeneous structure, and then we again cool the same steel in the furnace up to room temperature. Here also we get the coarse perlite as a output, which is a softer one. Okay, so see, for hypo means up to this we heat the steel above A3 line, and from 0.8 to 2% we heat the steel above A1 line. Just remember this difference, this will be asked in the exam. Okay, for hypo above the A3 line, for hyper above the A1 line. Okay, so next we have isothermal annealing. In isothermal annealing, see, we have a second diagram. This is not a iron carbon diagram. Okay, this will be simply a graph of temperature to time. Okay, see, this is a room temperature, and this will be a temperature for mean, we can say 20 to 25 degrees Celsius. When I start heating, this will increase above the, this line will be a A1 line, that is 720 degrees Celsius. This line will be A3 line, means just we have shown the temperature. This will be A3 line, means this is a 910 degrees Celsius line. Okay, above this we will heat it. See what I saying here, steel is heated above the upper critical temperature line, that is A3 line, means we can heat the material up to or above the A3 line somewhere here, but this temperature will be lower than your melting point. Okay, next, it is hold at the same temperature. See, this is a holding time period. We can hold the steel for some time period, and then we cool the steel. See what we written here, the steel is rapidly cooled. We only rapidly cool the material in water only, or in a brine, or in a oil. Means we required a liquid media to rapidly cool the material up to what? Rapidly cool the temperature 100 to 150 degrees Celsius below the A1 line. Where is the A1 line? This will be the A1 line, and below this, up to this, we will cool the steel in a rapidly manner. Means we can cool the steel in liquid solution up to, say, somewhat 727 minus 100 degrees Celsius, means up to 610 degrees Celsius we can rapidly cool the steel. Again at this point I will hold the steel, and again I will cool it in a steady air up to room temperature. Means see, in first full annealing process, just we have the three processes, that is heating, holding and cooling, and in this process we have 5 steps. First, heating, we hold the steel, we cool it the steel, or we can have a rapid cooling, again we hold the steel, again we cool the steel. I mean, this will be a two-step cooling process or two-step holding process. Okay, means we first heat it, second holding, again cooling, again hold, again cool. So this will take some more time period than full annealing process. Where it is used, application of isothermal annealing is for medium and high carbon steel and for alloy steel. Okay, so this is what we had seen in the first lecture. We have seen about the what is annealing. Annealing is a softening process, and we have two types, that is full annealing and isothermal annealing, and the next two types will be like process annealing and spheroidized annealing will be, we will see in the next lecture. Okay, so thank you one and all.